All right, so to finish up this section in our discussion of limits, so we got one more topic to talk about. What we're going to talk about is limits at infinity. So we're looking at how a function behaves at either infinity or negative infinity. All right. To begin this, what you have to know from your background, you have to review what do we mean by a horizontal asymptote of a rational function. That's kind of the key thing we're going to look at. Typically, in college algebra, pre-calculus, you learn about asymptotes. So this is sort of a reminder of how you look at different asymptotes. First of all, a vertical asymptote, that's always going to occur where the simplified function is undefined. So typically what you're doing is you're looking at where the denominator is equal to 0 after the rational function is simplified. Okay, a deleted point, let me talk about this a little bit. A deleted point, and a lot of times I just call this a hole. It's represented by just an open circle. Basically, the factors cancel out. So what happens is, like on this function, this is factors. See, this one would cancel out. So x equals -2 would be where that deleted point is, because x equals -2 makes this denominator 0. And then the leftover one, this part that doesn't cancel right here, the x equals -5, would be where you have a vertical asymptote. We'll look at some examples on that. Okay, so now let's talk about the key thing is what is a horizontal asymptote. So there's really several ways to look at this. We're going to look at a couple of ways to do this. This is the rules that's helpful to learn how to do. So if the degree of the numerator is less than the degree of the denominator, then y equals 0. The horizontal line y equals 0, which is the x-axis, acts as a horizontal asymptote. Other possibility would be if the degree of the numerator is equal to the degree of the denominator, then it's a ratio of leading coefficients. And I'll do an example to kind of show you how that works in just a minute. So I think it's probably worth just writing out maybe an example of each one. So like for this one, I'm going to write out f of x equals, let's just say something like this. Let me put this kind of up here. So an example for number one would be like if you have f of x equals x plus 1 over x squared minus x, the horizontal asymptote would be y equals 0 because the degree of the top is 1 and the degree of the bottom is 2. Okay, since the degree of the top is less than the degree of bottom, that means the horizontal asymptote's the x-axis. Okay, an example of the second one here, number 2, would be something like f of x equals, say, 3x plus 1 over, say, 2x minus 1. Okay, the degree of the top and bottom, which just means the highest power of x, they're both equal. They're both 1. So we would conclude that the horizontal asymptote is y equals 3/2. That's what I mean by the leading coefficients. Okay, so that's you can quickly kind of see this in your head anytime that happens. And then the last thing, the only other thing that's possible would be the degree of the numerator would be greater than the degree of the denominator. Then you don't have a horizontal asymptote. You'll have an oblique asymptote, which just means the asymptote slants if the numerator is 1 bigger than the denominator. So an example of that one would be something like this. You could have g of x equals x to the second over x plus 1. In this case, you would have no horizontal asymptote because the degree of the top is greater than the degree of the bottom. Okay? So those are the cases. That's where we're going to look at this. We'll talk a little bit more about the y part of this graphically on this next example here. Okay, so what we're going to go ahead and do on this one to begin this is a rational function. So you want to make sure you understand when you have a rational function, okay? And the degree of the top would be the highest power of x. Degree of bottom would also be the highest power of x. So they're both degrees are 1. Since they're equal, we're going to conclude this. If you look at the function, we look at the ratio of the leading coefficients. Okay, so what I mean by that is the leading coefficient is the number in front of the highest power. So what you'd end up having is you would have y equals 2 over 1, or just y equals 2. That's going to be what you call your horizontal asymptote on the problem now. Okay, so we'll talk about what that means here. So before we get into the graphing of this, I want to show you kind of what happens on this. So the first thing you want to go ahead and do is just draw the line y equals 2, and then this is going to be your horizontal asymptote. And we'll talk about what that means in just a minute before we go to the graphing calculator. Okay, the other thing is, on this function, you have f of x equals 2x plus 6 over x minus 1. If you want to find a vertical asymptote, you can usually do this in your head. So the vertical asymptote is going to occur at what makes you have a 0 denominator. So you solve the equation x minus 1 equals 0. All right, so let's put a vertical asymptote on this. So we go to x equals 1, and then we put a vertical asymptote like that. So what you want to kind of make sure that you understand is when you have a rational function, you want to focus on the asymptotes if you're thinking about limits at infinity. Okay, so that's the idea. Okay. Okay, now before we go to the calculator, I'm going to show you kind of a sign chart approach to figuring out how this graph goes, which is useful. Okay, so let's do this instead of using the calculator, because we're going to do a lot of sign charts in this class anyway when we start talking about derivatives. So what we want to do is just draw a number line, and what we want to kind of look at is what's happening on this problem in different regions right here. So we have the vertical asymptote, x equals 1. We want to just analyze what's happening on that. The other thing is we want to look at the x-intercept. So the x-intercept, what you always do is you just set the function equal to 0, and then you solve the equation. Okay, so you can multiply both sides by x minus 1 to eliminate that fraction. And then what you end up getting is you get the equation 2x plus 6 is equal to 0. So that's 2x equals negative 6. Divide by 2, you're going to get x equals negative 3. So x-intercepts are always found by setting the function equal to 0, right? So what we want to do on that is we also want to look at x equals negative 3. And what we're going to go ahead and do is, since we know what the x-intercept is, you want to go ahead and just put a dot right there. Okay, that's your x-intercept. So what I'm going to do on this, what you need to understand, and it's real important, is anytime you have a horizontal asymptote, the graph as you go to infinity is just going to level off at that in both directions. So it's going to level off at that. Okay, we don't know if it's going to be above that asymptote or below it. That's what we're going to find out here in a minute. And then the other thing is, if you have a vertical asymptote, the graph always either goes straight up to infinity or straight down to negative infinity. So you need to understand that's how asymptotes work, all right? So what we're going to do is we're going to do what we call test points. So we're going to start by taking let's start out here. Take a number that's smaller than negative 3. It doesn't matter what you use, by the way, because you'll always get the same result, and plug that value into that rational function. So just do 2 times negative 4 plus 6 over negative 4 minus 1. Now, all you worry about is this negative or positive? So if you look at this, the numerator is negative because it's negative 8 plus 6. The denominator is negative. A negative divided by a negative is a positive. So that will tell you that the graph is above the x-axis. Okay? Everywhere, when you're to the left of negative 3, you're above the x-axis. So what that tells you then is the graph has to look like this. You already are going to be going through that intercept. The only choice you have is to be above the x-axis and then leveling off towards the horizontal asymptote, because that's the way horizontal asymptotes behave. Okay? All right. Next thing we'll do is pick a test point between -3 and 1. Take your pick. It doesn't matter. I'm going to use 0 because I like calculating with 0. Same thing. Plug into the function. So do 2 times 0 plus 6 over 0 minus 1. So that is a positive over a negative. Therefore, it's negative. What that means is you are below the x-axis. Okay, so in between -3 and 1 on this graph, you're going to be below the x-axis. And there's only one way to do this, like this. Now, I'm going to show you how to figure out the y-intercept. Then that graph's just going to have to go straight down like that. It doesn't have any other choice. Okay, so let's look at the y-intercept. And the way you do that is you set x equal to 0. So you go back to the function, which we have here, and you just do f of 0. So everywhere you see an x, plug in a 0. So that's 2 times 0 plus 6 over 0 minus 1. That's 6 over -1. So that y-intercept is the point 0, -6. Okay, so I'll just put a dot like that. And now the sign chart tells you that between -3 and 1, you're below, and you only have one choice. You have to go to that point, and then you have to approach the vertical asymptote at -infinity like that. So that's how you can reason out how the function works around an asymptote. All right, one last thing. We're going to see what happens to the graph out here when we're bigger than 1. So what do? Pick a test point. Any number you want to, bigger than 1, will give the same result. Okay, plug in to your function like we've been doing. So do 2 times 2 plus 6 over 2 minus 1. You have a positive numerator, a positive denominator. Positive result, so what does that mean about the graph? It means you're above, exactly. So, just as a good sketch on here, there's only one possibility. If you're above the x-axis, well, first of all, you can't go down to -infinity. The only thing that you can do around that asymptote is to go that way. And then you got to level off at the horizontal asymptote, and then you just kind of sketch that in. So that right there is a fairly accurate sketch of a rational function without touching my calculator. And I want you to know enough about how the math works so that you don't just kind of blindly press buttons on these problems, okay? That's what's going on. Really, in a function, you plug in values of x to find y values, and that's kind of the idea. So this is kind of a shortcut to doing that. All right, now what we're going to do next here is we're going to figure out these two limits, okay? So this one is saying the limit as x goes to -infinity. And all that means is what is happening to the graph when x gets smaller infinitely. Remember, the answer to a limit's a y value, so this is what this means. As you go this way, what's happening? The graph's leveling off at what value? At 2. So that limit would be equal to 2. Okay, that's the value, by the way, of the horizontal asymptote. All right. Okay, next thing is saying what is the limit as x goes to infinity? So what that's saying is what happens to the graph as you go infinitely to the right. So if you go infinitely to the right, what's the graph doing? Leveling off at 2. Okay, so if you're working with a rational function and you're going to do a limit at infinity or -infinity, you want to look at the horizontal asymptote. Now, I did a lot of work on this problem. If the question was just simply find this limit, you could do this in like 10 seconds or less, okay? All you see is, okay, it's a rational function, horizontal asymptote at 2, therefore that's the answer to my infinite limits, okay? And that's a guarantee if you establish that you have a horizontal asymptote. You could bypass all this other stuff I did and get the answer in like 10 seconds, seriously, okay? All this stuff was kind of helping you understand, hopefully, how that graph goes. So I'm going to close this example off with one more thing. I'm just going to put this in the graphing calculator. So the original problem was 2x plus 6. And notice I'm putting that in parentheses because you have to. All right. Anytime that your numerator has more than one term, you have to put it in a set of parentheses. Same thing with the denominator. Has 2 terms, put that in a set of parentheses. Okay. Put that in. You can go zoom 6, standard window. You should get the same thing we got. And see, we have a nice accurate graph. Okay, we found our intercepts. we found our asymptotes, and the sign chart told us kind of what we need to know. All right, so that's it. All right, and I want to show you one thing that happens on this. If you trace, you know, like if I go infinitely to the left, I mean, this is kind of a good way to see how the graphs go. What happens is you can see this y value as I go further and further to the left, that y value is getting closer and closer to 2, all right? And then it's going to stop. The tracing's only going to allow me to get, it'll just, well, hold on, it will keep going. Okay, it just kind of keeps going like that. You're going to find on there, if you keep on tracing, it just gets closer and closer to 2, okay? Another way to look at this is with your table of values. If you go second graph in your table of values, well, if x gets bigger and bigger and bigger, it's real easy to see on here. X gets bigger and bigger and bigger. You see what's happening? Well, that's getting close to 2. Okay, and the same thing if you go infinitely to the left. If you get smaller and smaller and smaller, look at these values. They're just getting close to 2. They will never hit 2, but they will get close to 2. That's the idea. Okay. All right, so a graphing calculator can help you visualize and understand what's going on these functions, okay? All right, so let's move to the next thing. Pause and review all the stuff I did if you need to, all right? Okay, so we're going to kind of look at different cases on this to begin with. And so let's start with this one. Again, we have a rational function. That's step one, really, is you got to make sure that you understand that we have a rational function. So the question is find these infinite limits. So since I want you to find an infinite limit, well, your thought process is, what is the horizontal asymptote? If I can figure that out, I know the answer to this automatically. And I don't even have to consider the graph. Okay, that's the idea. So the way you do that is the degree of the numerator. The degree of the numerator is the highest power of x, so that's 1. The degree of the denominator is the highest power of x, so that's 2. So here's what we learned. If the degree of the top, I'm going to write that as degree of the numerator or top, is less than the degree of the bottom or the denominator, then therefore you can conclude that that horizontal asymptote is y equals 0. Okay, so that would be the horizontal asymptote. All right, that's it. And that will tell you, by the way, the answer to these limits. We know it. Okay, we can conclude right now that as x goes to negative infinity, we head towards the horizontal asymptote. As x goes to positive infinity, we do that. Problem done. Okay, well, let's just put this in the calculator and take a look real quick and make sure it looks right to us, and then I'll have you do a graph on here. So I just put x, I don't need parentheses because it's one term, over x to the second minus 4, zoom 6, and that's what your graph looks like, okay? And we're only really all that just kind of considering what's happening on the as x goes to infinity, all right? And you can see pretty clearly on here as x goes to infinity, you can see it leveling off. X goes to negative infinity, you can see that's going towards 0. This way it's going towards 0 also like that, okay? So a couple of things that I want to take a look at on here too is the asymptotes go like this. The vertical asymptote, what you do is you set the denominator equal to 0. So that denominator is this. You can solve that equation by factoring. That's a difference of 2 squares. So you end up getting x equals negative 2 and x equals 2. So those are your vertical asymptotes. Okay, you can see that on the graph. So to start with, just go ahead and do this. Draw out your two vertical asymptotes. Okay, and remember what I said is if you have a vertical asymptote, there's 2 choices. The graph's either going to go to infinity as you get close to the asymptote, or it's going to go to negative infinity. You can clearly see how the graphing calculator showed that to us. Okay, the other thing I want you to do is go ahead and just put a dashed line for your horizontal asymptote. And then we're just going to sketch the graph on here, okay? All right, it's good enough on here. You can see the intercept, so let's just put a dot there, and then sketch. Same thing here, just sketch towards the asymptote. Same thing out here. And then from here, just sort of make a sketch, just so that you have a record of this. This area down here, it goes to negative infinity around the vertical asymptote, and then it levels off from underneath the x-axis like that. Okay? So you can look at your calculator, but if all I'm asking you to do is find the limit of this function, you can bypass the graph. It's just, okay, what is the horizontal asymptote? All right, that's how easy it is once you get the hang of what asymptotes are. Okay, all right, so let's move to the next one here. And again, I'm asking you for finding the asymptotes, or I'm sorry, the limit is x goes to infinity, so we call that an infinite limit, so we're going to do that. Okay, so step one is really, okay, we have a rational function. That's the key. You have to understand that this is a special type of a function. And then since you know it's a rational exponent, if you want to work out these infinite limits, then the whole question is, what is the horizontal asymptote? So you can review those three rules that I taught you. Okay, so what you would want to do is look at the degree of the numerator. The degree of the numerator is the highest power of x, so that's 2. Okay, the degree of the denominator is the highest power of x, so that's 1. Okay, so the rule goes like this. Okay, if the degree of the top is larger than the degree of the bottom, therefore we have no horizontal asymptote. Okay, so we don't have any. So what that's going to tell us is the graph's not going to level off. Okay, it's going to do something entirely different. Now I'm going to show you a couple of things on this to get you started here. And what'll happen in this case is the graph is either going to go this way or it's going to go that way. So the answer to these limits is either going to be, and this is another conclusion you draw, therefore the limit as x goes to infinity or x goes to negative infinity, the answer is either going to be negative infinity or positive infinity. So I'm going to show you how you can do this then. Okay, so here's kind of the idea of what you would do without graphing. Okay, so what you would do is, I'll kind of call this step 4 here. So on this first limit, since we're looking at x goes to negative infinity, just pick a number that's, out there, all right? And it doesn't matter what it is. Let's just pick something like x equals negative 100. Plug it in and calculate. So we're going to go 2 times negative 100 to the second. And you can use a smaller number if you want to, like this, minus 2 over negative 100 plus 1. Now, all you have to reason out is this negative or positive? If it's negative, the limit goes to negative infinity. If it's positive, the limit goes to positive infinity, okay? Well, what will happen on this is the numerator is going to be positive. Now, if you needed to use your calculator, you could. I know that this square is a real big number. That if you take square 100, you get 10,000. And then this whole thing here is going to be 20,000, which is way bigger than that. Okay, so you can reason it out in your head, which I prefer. Okay, well, that's a negative. Therefore, we are approaching negative infinity. So therefore, the answer to that problem is negative infinity. Okay, that's how you figure it out without graphing. All right. Okay, so by the same logic, we apply this. Okay, so let's do like x approaches positive infinity. So pick a big positive number. So let's say x is 100 this time. Again, plug into the numerator. So we have 2 times 100 squared plus 6 times 100 minus 2. All over 100 plus 1. So that gives you positive numerator. You can tell in your head that's positive. You can tell that's positive. It's equal to positive. Therefore, the limit is going to approach positive infinity. All right, so that's the answer. Okay, so see, you're trying to get independent of this graphically. And, you know, for higher math, if you're going to Calc 2 and so forth, I can think of times when you just quickly want to know what the value of the infinite limit is. Okay, so that's how I did that. So again, just kind of review what I did. Because the degree of the top was bigger than degree of bottom, I knew I had a horizontal asymptote, or did not have a horizontal asymptote. I have what's called an oblique asymptote, which I'll show graphically in a minute. And so and the key thing I told you is if you don't have a horizontal asymptote, then the limit as x goes to infinity is either going to be one of these answers. Okay, you can guarantee that. Okay, and that's on a rational function. So I just do test points to figure out which it is. Okay, all right, so think about that. All right, so let's graph this on the calculator. Let's go ahead and put that in. Let's put the function in and just see what this looks like. And I think this will help you understand this. So the limit, or the numerator, is 2x to the second plus 6x minus 2. And then denominator is x plus 1. Okay, and let's do a zoom 6, just a standard window. So zoom 6, and I'll show you kind of what happens. And I'm going to have you do a rough sketch of this, and I'm going to show you kind of what happens on this problem now. So first of all, if you wanted to look at one other thing on the graphing here, the vertical asymptote happens where the denominator is 0. So x plus 1 equals 0 gives you x equals negative 1. So we can start on this problem by drawing this. Okay, like that. Now you can look at this graph. So just take a look at this. Look at the left-hand limit. As we go to negative infinity, the graph is getting smaller and smaller and smaller. As we go to positive infinity, the function values are getting bigger and bigger and bigger. You can see this pretty clearly on your table of values. Okay, so just go infinitely to the left. Look what happens. Okay, this thing's not going anywhere. It's just getting smaller and smaller. That's going to negative infinity. Okay, if you do the limit as x goes to positive infinity, all that means is as x gets bigger, so does y infinitely. So it never levels off. So it's real easy to interpret these problems from their graph. Okay. Right, and what I'm going to show you is one other thing that I'd like you to know something about here. The sixth kind of part of this problem is I'm going to show you anytime the degree of the top is bigger than the degree of the bottom by 1, then we get what's called an oblique asymptote. And you can do long division to figure this out. Okay, so you get an oblique asymptote. So what I'm going to have you do is we're going to do this. We're going to do 2x squared plus 6x minus 2, and we're going to divide by x plus 1. Okay, let me give myself a little bit more room. And of course, this is stuff that generally in college algebra you learn, or pre-calc, you learn how to do long division. Okay, so we have 2x squared plus 6x minus 2, and then divide by x plus 1. Now, this is something you may have to review. If you're going to take Calc 2, I can think of times when you do long division, either synthetic division or just standard long division, so you have to know how to do both. Okay, so I'm going to review this, and if this is something you don't understand, then you might want to just do, go to YouTube and just search algebraic long division, and you'll probably find some videos that'll do that. I probably on my YouTube channel have something on there somewhere too, so you could do a search on my YouTube channel. So what you do is you do this, okay? You ask yourself, what do you multiply x by to get this? Or you can say, okay, 2x squared divided by x. Okay, that's equal to 2x. Okay, so what goes here then is 2x. All right, that's step 1 is you do a division. Step 2 is you multiply. So you do 2x times x plus 1. So that gives 2x squared plus 2x. And they're both positive values, so you put that underneath the like terms. Okay, Step 3 is you subtract. This is, to me, is where students mess up, is this. So you go 2 minus 2, that's nothing. That's 0x squared. You don't even have to put anything there. 6 subtract 2 would be 4x, like that. Okay? And then you don't have to put this. I guess I was just putting that for, mostly for emphasis, so you can just put that like that. Okay? All right, and then the last step is you just bring down the next number. Okay, so if we do that, we bring this down, and then we just go through the loop again. All right, so now it would be 4x divided by x. I start over again, so it would be 4x divided by x is 4, and it's a positive 4, so that goes there. And then you multiply. 4 times x is 4x. 4 times 1 is 4. You subtract. So when you subtract, you're going 4 minus 4 cancels. This always will. And then you're doing negative 2 minus 4, so that's negative 6. So it turns out that this thing right here is what we call the oblique asymptote. So I'll kind of call this step 6. The oblique asymptote is y equals 2x plus 4. Okay, so let's graph that. Now, we don't need the calculator to do that. We'll do this on the graphing calculator in a minute. So the y-intercept's 4. You have a slope of 2. So you would go up 2 over 1, up 2 over 1, and then you can kind of go backwards. Down 2, left 1, down 2, left 1, and so forth like that. And then just kind of sketch that in. It's an oblique asymptote just means it's a line that slants with some positive or negative slope. So that's how that goes, okay? All right, I'm going to get out my calculator, and we're going to do this last thing to kind of finish this up. So I'm going to go to y equals, already got the function in. I'm also going to have you put in 2x plus 4 so you can see what happens. Okay, what do you notice? Okay, what does it look like the function's doing? As x gets bigger, what is it getting close to? It's getting close to that asymptote. Okay, so if you want to do this, you could do zoom out like this and see how that, I would hope that makes it kind of clear. It's just, they almost become the same thing. Okay, so that's the idea. All right, I'm going to go back and do a zoom 6 just for a standard window. Okay. All right, now the rest of this, I just want you to sketch on this, and that'll be good enough. I'm not going to worry too much about what the intercepts are, just trying to give you the idea. So that graph's going to do something like this. It's going to swing down and approach the asymptote like that. And then over here, it's going to do something kind of like this. So you're going to touch, it looks like you touch the x-axis around there. You swing up towards the vertical asymptote, and then you approach the oblique asymptote like that. Okay, so there is an asymptote there. There's a vertical asymptote. And again, the graph is going to infinity and negative infinity around that asymptote. So that's the idea. Okay. All right, so let me kind of summarize this a little bit. First step, it's a rational function. Second thought process, do I have a horizontal asymptote? Because degree of top is bigger than the bottom, the answer is no. So then it kind of becomes, okay, do I have an oblique asymptote? Regardless of whether you do or not, the answer to these limits will either be negative infinity or positive infinity. That's a guarantee. So what I showed you to do on a limit as x goes to negative infinity, pick a small negative number, plug in. Okay, the calculation turned out to be negative, therefore the answer is negative infinity. On a positive infinity, you're approaching positive infinity, pick a big positive number, plug it into your function. All you care about is whether it's positive or negative. Since it's positive, that goes to positive infinity. And then you don't even have to think about the graph. I mean, that's how you do the limit without a graphing calculator. You want to review the long division because that's going to pop up here a little bit in this class and in future classes, okay? All right, so here's what I would like to have you all do here on this, and I'm going to probably erase some of this now. So if you need to pause and get any of this stuff down, do it now. And I'm going to go ahead and erase some stuff here. So, all right. Okay, so go ahead and see how many of these problems you can do without even thinking about the graph. They're all infinite limits. So the question is, the whole key is horizontal asymptote. These problems, if you caught on, you can do pretty quickly, okay, without graphing. So I'm going to pause, let you come back, and when you're done, check and see if you get what I get. All right, moment of truth. See if you got this right. All right, here's my answers. Again, notice I didn't graph. Okay, I don't need to graph. So this one, the horizontal asymptote is 3 over 2. Therefore, that's the limit's answer. That's because the degrees are the same. Okay, degree of top is equal to degree of bottom. Have the horizontal asymptote. That's the answer to the infinite limit. Either way, too, negative infinity, positive infinity. Part B, there's no horizontal asymptote because the degree of top, being 3, is bigger than the degree of bottom, 1. Okay, so the answer is infinity or negative infinity. That's a guarantee, so use a test point. I used a big positive number. Okay, when I plug it into the function, I get a positive value. Okay, I don't need to crunch it out. I just need to know whether it's positive. So therefore, the answer is positive infinity. Okay, next one, degree of top is 1. And that's less than the degree of the bottom, which is 2. Therefore, you conclude that the horizontal asymptote is 0. Therefore, that's the answer. Guarantee. And that would apply regardless of whether that's approaching negative infinity or positive infinity. Part D is really the same as Part A. Degree of top and bottom are the same. So there's your horizontal asymptote right there. 2/4 reduces to 1/2. Therefore, that limit, infinite limit, the answer is 1/2. Okay, so that's kind of ultimately how you would do the problems. A lot of the graphing and stuff we've done is to kind of help you understand those concepts and how they work the way they do. Okay, that's the idea. Okay, so very good. Let's move to the next page. The next page is sort of a review of something you typically learn in college algebra or pre-calc. If you don't know this, then you want to definitely know this then. So a lot of times when I teach college algebra or pre-calc, I kind of teach these as dance moves. So we're going to look at what we call endpoint behavior of polynomials. So a polynomial, an example of a polynomial would be something like this. You have 2x to the third plus x to the second minus 3x plus 4. What a polynomial essentially is you have your variables x, and those exponents are whole numbers. So these exponents, even that is an exponent of 1. Technically, this part right here would be x to the 0 power. That's kind of a good thing to think about there. And what you always have is these things are separated with sums and differences, and you can have coefficients. You can have any number you want to in front of the variable x. So that's what a polynomial looks like. So it turns out that the graphs have 4 different possibilities. All right, so we're going to learn what we call the leading coefficient test. Now, the leading coefficient is this thing right here. Okay, it's basically the number in front of the highest power. So that thing right there is your leading coefficient. And that tells all that you only got to look at 2 things. You look at the highest power, and you look at whether that's odd or even. Okay, it can be one of the 2. And then you look at the leading coefficient, whether it's negative or positive. That's what makes a difference. So what we're going to do is I'm going to show you all the possibilities down here then. So first of all, we're going to consider when the highest power is odd on both of these things right here. And I'll give you an example to write down of each one. So let's construct a function where the leading coefficient is positive. Let's say like 2x to the 5th, and it doesn't matter what's beyond that. You could have anything you want to. All you look at is the highest power. Okay, so you could have x to the 4th, blah, 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 whatever. Okay, that doesn't really make any difference. This is what makes a difference. So what happens is if you have this, if it's odd and the leading coefficient is positive, then the graph looks like this dancer. So it kind of, as x goes to infinity, y goes to infinity. As x goes to negative infinity, y goes to negative infinity. What happens in between doesn't make any difference to us, okay? It can loop, it can just kind of connect, but there's no breaks like that, okay? So what we would conclude on this then is we would find the limit of this function as x goes to positive infinity would go to positive infinity. So as we go this way on the x-axis, y goes this way. And then vice versa, if you're doing the limit of the function as x goes to negative infinity, then this graph goes to negative infinity. Okay, so as we go to the left, x goes down. Okay, that's how it goes. It's automatic. So again, you're going to know these infinite limits by your knowledge of how polynomial functions behave. Okay. Second possibility would be this. Okay, let me give you an example to write down on this. Say that you have f of x. Again, we want to look at a odd power, so let's say 7th power. And then let's put a negative number in front. Okay, and then again, what goes past that does not make any difference whatsoever. That does not affect the endpoint behavior. Okay, getting a phone call from a scammer, robocall. Go away, robo. All right, so let's see. This goes like this. So it turns out if you have this, if you have a odd degree polynomial and the leading coefficient's negative, then the graph looks like this disco man here. Right? So it kind of goes like this. So the graph turns up like this, turns down like this. What happens in the middle, we don't care about. All right? So the idea would be if you were doing the limit of this kind of function as x approaches infinity, as x goes to infinity, y is going to go to negative infinity, so you get that answer. And then the limit, f of x as x goes to negative infinity, well, you're going to do this. If you go that way on x, y gets bigger and bigger infinitely like that. Okay, so that's how it goes. Just think of your odd degree polynomials look like these two dancers. Okay, their arms are going in different directions. That's the idea, okay? So let's do the other two cases, all right? So on this, now we're going to consider what happens if we have an even degree polynomial, leading coefficients positive. So let's write down this example. Let's say we have f of x equals x to the second. I'm just making something up here too, okay, minus 7, something like that. Okay, so that's got everything we need. It's an even degree, and then the leading coefficient in this case is positive. Let's put a number in front. It doesn't matter. It's positive. So what's going to happen on this is the graph looks like this, kind of ballerina here. Okay, so it goes like that, goes like that. It's kind of like a parabola. Again, you may have some looping here, may touch the x-axis depending on how high that power is, but that is not what matters. That stuff doesn't matter. That's what tells you the answer. So what you would have is the limit of this function as x approaches positive infinity would be positive infinity. That just means as x goes this way, y gets bigger and bigger. Okay, so that's infinity. Same thing here. As x goes to negative infinity, y gets bigger. So we would conclude that the limit f of x goes to negative infinity is also infinity. Okay, all you got to do is just look at the polynomial and know the rules. Okay, I'll kind of show you with this little Desmos thing here in a minute, something that's kind of cool to look at too. All right. One more possibility. So if we have still working with an even degree, highest power is even, this time leading coefficient's negative. So here's an example. F of x equals negative 5 x to the fourth. Remember, the rest of the stuff does not matter. So what would happen on this is the graph would look like this dancer. So the graph would go like this. Again, what goes on in the middle, we don't care about. So what you would have is you would make this conclusion. So the limit f of x as x goes to positive infinity would be negative infinity. X goes this way, y goes that way. And then if you go to negative infinity, so as x goes to negative infinity, x goes this way infinitely, y gets smaller and smaller infinitely like that. Okay, so those are your rules that you have. There's 4 possibilities. Nothing else is possible. Okay? So what I want to do then is I want to go up to this Desmos thing here. And I want to open this up. And this is just kind of a good thing to show students on here. Right now, look at this. Highest power is 4. So that means it turns up or it turns down. The number in front, the leading coefficient is positive, so it turns up. I can kind of zoom out on this, and Desmos is a pretty cool applet generator here, so that's what that looks like. Okay. What? Ah, dang it. Crap. There we go. Okay. Now be real careful how you do that. All right. Let me show you what happens on this. Okay. If I was to put a negative on here, well, look what happened. Okay. The graph now just turns down. Okay. And it won't make any difference, if I make this exponent, as long as that exponent's even, same result. Okay. Even exponent turns down. If I go back and if I put a number, a positive number in front, now it turns up. So that's how that goes. If I change this now to an odd degree, oh, look what happens. Okay, let's make that a 5 like that. Okay, so what happens? The highest power is the odd. Number in front's positive, does this. Okay, if I change that 2 to negative, look what happens. Okay, so that's what happens on that. So I like that Desmos app because it just kind of allows you to experiment a little bit and see how these things work then. Okay. Okay, so what I want you to do is this basically. There's 4 problems I want you to do. So what I want you to do is sketch a graph, kind of like I was showing you, and then fill out these limits. You don't have to put anything in your graphing calculator. I don't want you to have to do that. I want you to just quickly know what the answer to these limits is. So you want to go ahead and pause the video when you're done. All right, go ahead and check and see if you did what I did. Okay, and move ahead if you're ready. Okay, so let's see. This is leading coefficients negative, degrees odd. Therefore, the graph looks like this. That would mean as x goes to negative infinity, the graph goes to positive infinity. As x goes to positive infinity, the function values go to negative infinity. That's it. Okay, this one has a even degree, leading coefficient's positive, number in front's positive. Graph looks like this. Therefore, the limits, both of them are going to positive infinity. Remember, the answer to a limit is where is y going? Y is going to infinity. Both places. Okay, this one is a odd degree, positive leading coefficient. The graph looks like this at the endpoints. So as x goes to infinity, y goes to positive infinity. As x goes to negative infinity, y goes to negative infinity. Okay, that's what you learn. Next page. Should have got this on this last example. This one has an even degree of 2, leading coefficient negative. Graph turns down like this. Therefore, both limits go to negative infinity. That's the idea. Okay. So again, these things are easy to do if you know the rules and understand how those functions go. You don't have to touch your calculator, and that's the goal. Just quickly do these problems. Do them in your head. Okay? All right, so let's see. One last thing, and this will wrap this up. I just want to go over this. Now, I'm going to have you all also do this example yourself. So I would like you to pause the video and see if you can reason out what these limit values are based on the graph I gave you. Okay, pause. Okay, check your answers. See if you got what I got. If you got it, you're done. Okay, if you need to listen to explanations, just hang out for a few minutes. All right, so this one is the limit as x goes to infinity. Okay, all that means is x is getting bigger and bigger. So I just sort of trace it out. Well, you have a horizontal asymptote. That value of that horizontal asymptote is -2, therefore that's the value of the limit. Okay, this is an infinite limit as x goes to negative infinity. So as x gets smaller and smaller, y gets bigger and bigger. So that thing right there just takes off towards positive infinity. So that's how those are the infinite limits. These two things we call these, limits at infinity. And what you're typically doing is, remember, that's all about asymptotes. It's all about horizontal asymptotes, oblique asymptotes. Okay. Now these things right here, these are all around too. So this things right here, these would be what we call infinite limits. And you'd have this, okay, so this is a right-hand limit around the asymptote x equals -2. So if it's right-hand limit, you're just doing this. Get to the right, follow the graph. Where's it going? That graph is going to -infinity. This is a left-hand limit. Get on the left of -2, start closing in. That thing, where's it going? It goes to positive infinity. Okay, this is a two-sided limit. Those things are different. They're going to different locations. Therefore, that does not exist. Okay, and then these last three, same thing. These are infinite limits. It's because you have a vertical asymptote. And remember, if you have a vertical asymptote, they're going to have this situation. Now, it's a little different on this one. Typically, I told you that typically in a function that I give you, if I give you an algebraic function, then you can guarantee that it either goes to infinity or -infinity. Now, this would be more like a piecewise function. So if it's a piecewise function, you might have a little different situation around your vertical asymptote. Okay, so what happens? This is a right-hand limit. If you get to the right of 2, where's the graph go? It goes to infinity. Okay. Left-hand limit, trace it out, get to the left of 2, where's that go? That goes to 0. Okay, since those are different, the two-sided limit does not exist. Okay, so that's it. That'll be kind of, this part of the lecture was dealing with limits infinity and infinite limits. Very easy to do if you know the rules. Okay, good luck.